yay! It was great, the screen is weird on this. Fractals. What are they? Okay, this is the definition that you guys should all write down. Fractals are self-similar mathematical sets with separate fractal dimensions that exceed the amount of space that the fractal occupies. Probably makes little or no sense.
You don't need to write.
Yes. What are these? Alright, so a fractal are those weird shapes that you see in presentations like that one over there, and all around the math department, and also in my presentation. So for example, this is a fractal. I don't know how to make one that good, but I can make one of the more basic ones. Self-similarity, so that's this one here. It's when an object looks like itself, and that might seem a little, doesn't everything look like itself? A self-similar object will have smaller copies of itself embedded in itself. So, for example, this thing has a bunch of an hexagon, but if you look closer, it's got more little hexagons, and then even more little hexagons. So that's self-similar. A mathematical set. I'm guessing a lot of you have heard of sets at one time or another. They are a collection of objects or things that are collected together, and you can deal with them as one object. And that object has the properties that all of the objects have in common. So, it's nice to deal with that. Yeah. And then the fractal dimension. Things get pretty good. New slide. I'm not gonna, it would take too long to explain. That's it. So new slide. So the fractal dimension describes how complex a fractal is. So the more infinite the perimeter of the fractal, the larger its fractal dimension is. So I'm going to start with the example that is most commonly used to explain this, the length of the coastline. So there's a map of the continental U.S. and the non-continental U.S. anyway. Let's look at it. So with the dark blue measure, we use one length of a stick, one length rule, and we get a measurement. And then we use the light blue one, and we get a smaller one because it's a smaller. We get a larger measurement because it's a smaller stick, and the red one's even smaller, so the coastline becomes longer and longer. So, and as the ruler gets smaller, the coastline measurement actually gets longer because you can keep measuring around little bits. So long as there are more details, the coastline stretches. The length of the coastline increases towards infinity. And fractals have that same thing going on. So the fractal dimension measures how complex it is. To find its measurement, a fractal's measure in the fractal dimension, you take the length of the perimeter and divide it by the area of the fractal. And that ratio shows the length of the fractal. So there's a lot of different ways to get fractals. I'm going to explain two of them right now, using a function. So these fractals forms, so they take shape and then they form a smaller copy. Like this function generates another copy of the fractal, and inside that there's another, and the equations are really, really complicated. So they make my head swim. I'm not going to go too deep into that. Subdivision's a lot simpler, and if you want to make a fractal, I recommend this method because it won't make your head swim. So you take a shape, or two shapes, or three shapes, and you do something to that shape, and now you have more of those shapes, and they're a little smaller. And so you do the same something to those shapes, and again, and again, and again. And eventually, you end up with something like this simple fractal. Here. So you took a square, and you put four squares on it. Now each of those get divided into this, so they take these out. This isn't a very detailed picture because the resolution is terrible, but it does show how detailed these things can get. Hard fractals. So this is the Mandelbrot thing. Two circles and another circle, and then on that circle there's more circles, and it keeps going and it's really weird. And a weird fractal. And a fractal in nature, ferns. So each leaf on a fern, on this fern, is a replica of that fern, and on and on and on. And fractals can be in 3D too, for example, this one. Yeah. And there's so much more that we could have explored, but we don't have time. So, I forgot. Now let's see.
So, my part of this presentation was to write, I was going to write the program to draw a circumscribed triangle, but I got sick of it as soon as I ran out of time. So I'm going to show you someone else's code of that. So a circumscribed triangle is a triangle that starts as one big triangle, and it draws a line from the midpoint of each side to the midpoint of the opposite side. So it goes like this.
And new triangles. And you can keep going forever.
So, and that'll go infinitely.
But he doesn't.
Can't really see much further than that. So, and then, so Matt showed us a different website earlier this week that showed that you can draw a circumscribed triangle by going like this. So if you have a triangle, then you take a random point anywhere in the triangle. So say I choose here, and you go halfway to any corner.
Can we borrow your dice, Matt? Your dice?
So you have three random corners. So you pick a random corner, you go halfway to that corner. You go halfway to one, and then go halfway to two. Go halfway from there to three. So roughly like that. And if you continue going like that for long enough, it will draw a circumscribed triangle.
Not with the lines, but with the points.
With the points, yeah.
So that's kind of misleading.
Yeah, that's right. But so if you
and it takes several thousand iterations to get a really good model, but it is really cool if you can, if you take the time to see it all out. Except you'll have one point often that sticks out.
The point you start with can often be in the middle of one triangles. But I think we're done.
We're done. That's it. Questions?
For the circumscribed triangle, like with the dots,
Yeah.
what would it look like after like a lot of?
After a lot of dots?
Like,
After like you went on for a really
so it would
long
look
time.
like.
Actually, you don't need a lateral triangle. You can use any triangle. It'll still work. But it starts to look like.
It would look like.
It would look like that.
This triangle.
Okay.
It does. It starts. That's the circumscribed triangle. And eventually, I'm not gonna. It's kind of hard for me.
The dots would fill in all of the blue areas,
Oh, okay.
essentially.
Okay.
And they would
Right.
leave the white spaces open, which is
Really neat.
hard to visualize, but if you did it,
We
like,
can't. We
like
didn't
that.
find those from.
Actually, Campbell, what you just drew is a good representation of what that program does. Because
This
it
is what
does,
it
it just
looks like in the
plots
first
dots. The thing about fractals is it's connected sort of directly to what's called chaos theory, where something like that seems completely random to go from a random position to a random corner. Why would that create anything that looks like a pattern? But it does. It looks like, in fact, it does create Sierpinski's triangle after thousands of iterations.
I think I found it.
As soon as it loads. Anyway, while that's loading, any other questions? No. Nothing? I'm just gonna wait for this to load. And, internet will need you.
Can you do fractals without computers? I mean,
You can.
the way you just did that
Just-
one would have
yeah,
worked, but
absolutely.
Draw.
It's a lot harder,
And I mean, simple ones you can draw.
like the surface
easily.
triangle. But
Or-
you straight edge and a compass would be good.
Yeah. Or if you
And
just
with protracted.
want to draw like a tree.
oh yeah, right.
Just branch it off smaller and smaller.
But for example, that one up on the board, that
Right.
means
Good example.
Alright,
Any other questions?
oh, here we are. Chaos game. Yeah, that one.
More loading probably.
That's not a question, that's just tricks.
It's not gonna do it actually.
It's just, wait, no, I feel like we've seen this.
This is not the site we were on before, I believe.
Oh, that is the game, yeah.
Wait, yeah, that's the game.
But it's not gonna.
So when you go towards one vertex or the other, you get either red, green, or blue.
Anyway, I don't know.
Yeah, we're not gonna connect, yeah.
We'll look for it and send it, we'll post it on the conference and see if we find it.
Okay, thank you. Now we have